We now have all the ingredients to calibrate an interest rate model to market data. More specifically, we calibrate a two-factor Gaussian hystermorton model to market data consisting of swap rates and at-the-money cap quotes. For that, we first derive pricing formulas for caps in Gaussian AGM models, and for the calibration we need the appropriate objective function to be minimized, and we will see that a good choice for weights of pricing errors are the vegas, the derivatives of the Black and Bachelier prices with respect to their volatility. Let us review the pricing of caps. We consider a spot date T0 that we set to 0 for simplicity. We then consider a sequence of reset and settlement dates T0, T1 up to Tn and assume that they are all equidistant with difference given by delta. We are also given a cap rate kappa. Recall that the ith caplet that resets at time ti minus 1 and settles at time ti is equivalent to 1 plus delta k kappa times the put option on a ti bond that expires at time ti minus 1. The price of the ith caplet, therefore, is given by the Q expectation of the discounted payoff of this put option on the TI bond. Now suppose the underlying model is a Gaussian AGM model, and recall the bond put option price formula in such models. That gives us the price of the ith caplet as shown here, where capital phi is the standard normal cumulative distribution function and the parameters d1 and d2 are given as shown here in terms of the integrated T-bond return volatility V. Now consider more specifically the following two-factor Gaussian HGM model with a volatility specification as shown here, where V1, V2, beta 1 and beta 2 are real parameters to be calibrated to cap market data. Elementary integration shows us that in this case we obtain the following expression for the integrated volatility terms in the option price formula. We now want to calibrate this two-factor Gaussian HGM model to swap and cap data given at the spot date T0. More specifically, the given data consists of spot swap rates with swaps that pay annual fixed coupons and at the money cap quotes where the caps have semi-annual cash flows. The procedure is the following. We first estimate the discount curve from the swap data. Second, we then calculate the forward swap rates with semi-annual fixed payments. These correspond to the at-the-money cap rates. And then third, we minimize the weighted squared cap price errors for calibrating the volatility parameters V1, V2, beta 1, beta 2. Here is the swap data. We have swaps paying fixed annual coupons with length ranging from 1 year to 30 years. Swap rates are given in this column. The first quote is the 6-month simple spot rate. For the valuation of the caps in the model, we need the discount curve at the semi-annual frequency. We use the exact method based on the pseudo-inverse to estimate the weighted increments of the discount curve. Delta, as shown here. The estimated discount rates are given in this table. We then compute from this discount curve the 6-month forward swap rates whose first reset date is T0 equal to 1/2 and that have semi-annual fixed payments. We derive these swap rates from this well-known formula. The figure on the right-hand side shows these forward swap rates as function of their maturity, which ranges from 1 year to 30 years. These forward swap rates give us the at-the-money strikes of the corresponding caps with maturities ranging from 1 to 30 years. The corresponding prices of the caps are given as nominal prices and equivalently in terms of their black implied volatilities and in terms of their normal implied volatilities. Recall that these caps have semi-annual cash flows. The calibration problem now consists in finding the remaining parameters V1, V2, beta 1, beta 2 that we summarize by theta, such that the model cap prices that we denote by C hat theta n for the nth cap are as close as possible to the market cap prices Cn shown on the previous slide. We minimize the mean squared error of the implied volatilities rather than of the nominal prices. The reason is that the black and normal implied volatilities, they standardize option prices, they're more robust over time and better comparable across maturities and strikes. The problem is that computing implied volatilities involves numerical inversion of the black or Bachelier formula at each minimization step, and that is computationally costly. Fortunately, there is an easy way out as shown on the following slide. We make use of the vega, the derivative of the black or Bachelier cap price with respect to the volatility. A first-order Taylor expansion of the black price function Cn then gives us this relation, where sigma hat theta n denotes the model implied volatility and sigma n is the market implied volatility. We can then express the squared implied volatility error as a weighted squared cap price error as shown here. Now the good news is that there exists a closed form expression for the vega in the black and the Bachelier model. Recall that the black price of the ith caplet is given as shown here, where capital phi denotes the standard normal cumulative distribution function and the parameters d1 and d2 are given as shown here, and we write fi short for the forward rate as shown there. Elementary calculus using this identity then gives us the following expression for the derivative of the caplet price with respect to the volatility parameter sigma, the black caplet vega. By linearity, the black cap vega is then simply the sum of the black caplet vegas as shown here. Similarly, we recall the Bachelier price formula for the ith caplet shown here, where capital phi is again the standard normal cumulative distribution function, and small phi is the density. The parameter di stands for this, where fi is shorthand for the forward rate. Elementary calculus again, using these identities, give us the following expression for the derivative of the Bachelier-Caplet price with respect to the volatility, the Bachelier-Caplet-Vega. Linearity gives us the Bachelier-Cap-Vega as the sum of the Bachelier-Caplet-Vegas. Using the Bachelier-Vegas, the calibration problem now boils down to the weighted least squares problem shown here. Using standard optimization libraries, such as the MATLAB built-in fmin search, we find the following values for the parameters. We obtain similar results using black Vegas instead of Bachelier Vegas. On this slide, we see the fitted normal and black implied volatility curves. In black, we have the market quotes, and in red, the model implied volatilities.